Neurolinguistic programming rests on three pillars: the language we use, the sequences of our actions, and the neurological networks that build our thoughts. But to understand human behavior at its root, we have to strip away the linguistics and the programming. We need to isolate the neurology. This brings us to a strict biological constraint. The human brain is sealed inside a dark, silent vault of bone. It does not interact with the objective universe directly. This creates the core axiom of the entire model. The map is not the territory. The reality you experience is not the actual world. It is a map your nervous system sketched out to help you navigate it. Think of the brain as a narrow-band receiver. It evolved to keep the organism alive, not to perceive absolute truth. At any given millisecond, the physical environment is flooded with an infinite spectrum of data, like electromagnetic waves, shifting air pressures, and chemical traces. Yet, our sensory organs are physically capable of capturing only a microscopic fraction of it. Because we are locked out of the full spectrum, what we experience as reality is actually a highly edited, internally generated simulation based on that slice of captured data. Since we only ever interact with this neurological map, understanding the mechanics of how that map is built is the only way to understand human behavior. To get from raw external stimuli to a cohesive internal map, information must pass through a strict cognitive pipeline. If the brain tried to process every photon and sound wave that hit the body, the nervous system would overload. To prevent this, the brain uses aggressive gating algorithms. This diagram illustrates how disorganized data points slam into a three-tiered gating mechanism. The first tier is deletion. Deletion actively drops any environmental data that doesn't serve the organism's immediate survival needs or current values. When you focus on a task, the ambient temperature of the room is often deleted from your awareness. The data that survives drops to the second tier, distortion. Distortion bends incoming raw data, forcing it to fit into pre-existing psychological frameworks. It is the mechanism that allows two people to look at the same facial expression and see either anger or confusion, depending on their expectations. Finally, the remaining data hits generalization. This algorithm takes a single past instance and uses it to classify an entire category of future events. After one bad experience with a specific animal, the brain may generalize that the entire species is a threat. By the time data makes it through these three algorithms, it is heavily redacted. Human consciousness operates on a highly distorted subset of reality. So what happens to the data that survives the filters? The brain does not store this information as abstract code. It translates the data into primary sensory representations. This model tracks how the data flows into distinct pipelines: visual, auditory, and kinesthetic, or physical sensation, alongside olfactory and gustatory channels. Within this model, every internal thought, memory, or projection is constructed as a sequence of these generated sights, sounds, and physical sensations. To retrieve these stored memories, the brain typically uses a lead system, a single dominant sensory channel that pulls the rest of the file. A specific mental image might trigger the audio memory of a conversation. For conscious processing and communication, individuals rely on a preferred system. Someone with a visual preference might say, "I see what you mean," while an auditory thinker says, "That sounds right to me." A person's psychological state is tied to the specific sequence and type of sensory representations they are currently generating. We can break these representations down even further by isolating a single sensory channel. Inside a visual or auditory pipeline, the data is coded with granular parameters called submodalities. This dashboard shows the visual channel. The submodalities are the specific qualities of the internal image: its spatial location, its brightness, the saturation of the color, and the sharpness of focus. There is a direct mechanical relationship here. As a submodality slider moves, for instance, if the image gets brighter or closer, the intensity of the internal experience changes. These structural qualities are the actual triggers for the body's autonomic nervous system. Your heart rate doesn't spike because of the story you're telling yourself. It spikes because the mental picture is large, bright, and close. If you take a memory that causes anxiety and mentally push the image 20 feet away, draining it of color and blurring the edges, the physiological response drops. Behavioral change follows from tuning these underlying submodalities, rather than just arguing with the logic of the thought. So what part of the brain manages these millions of submodality sliders? This diagram compares our processing bandwidths. It shows that conscious attention can only hold about 7, plus or minus 2, chunks of information simultaneously. This bottleneck restricts our conscious awareness to present-moment processing and slow linear logic. Below that narrow pipe is the massive network of the unconscious mind. This is where the bulk of sensory processing, memory storage, and physiological regulation occurs. The unconscious operates outside direct linguistic control. It doesn't process negatives or abstract words. It processes symbols, emotions, and primary sensory channels. This explains why you can consciously know that flying in an airplane is safe, but still experience a panic attack. The logic is stuck in the narrow pipe, while the autonomic response is driven by the high bandwidth network. Because the conscious mind lacks the bandwidth to process complex submodalities, neurological intervention must target the unconscious structure. We can now trace the complete cognitive pipeline. Raw data hits the filters of deletion, distortion, and generalization. The surviving data is encoded into sensory channels, tuned by submodalities. This zoomed-out view reveals a feedback loop. The emotional state that emerges at the end reaches back to the beginning, actively tightening or loosening the initial epistemological filters. If the pipeline generates anxiety, that state feeds back and tells the deletion filter to drop all calming data, while distortion looks for threats in neutral events. This creates a self-reinforcing mechanical process. From this perspective, an unresourceful psychological state, like a phobia, is a structural error in how representational systems are sequenced. This is why practitioners bypass linguistic debates to focus strictly on dismantling the neurological parameters driving the loop. In this model, the human mind operates as a specific mechanical encoding engine. Intervention is achieved by altering the structural parameters of an internal representation. We only ever interact with the map. When you change the structure of that map, you change the subjective reality of the territory.